All right, so hopefully you've looked up your data, and for air, the viscosity is 184.6 times 10 to the negative 7th Newton second per meter squared, and the density is 1.1614 kilograms per meter cubed. So hey, so is that going to be turbulent? Well, we can start by comparing the density to engine oil. Engine oil is a lot denser. So if we look at our situation, for air, it's low density, so there's going to be hardly any air going through there compared to engine oil. There's going to be a lot more mass flow rate for the engine oil, and that would make us believe that engine oil would be more likely to be turbulent than air. On the other hand, looking at the viscosities, engine oil's viscosity is 0.486. You can get that from the tables, and that is huge compared to the viscosity of air. So there's a lot of cohesion between adjacent engine oil molecules, which would make turbulence less likely. Okay, so we would go ahead and do the let's go ahead and, you should go ahead and get your calculations for your Reynolds numbers. Note, I have had some students in the past say, look, I have the formula on my formula sheet, I'm just getting it wrong because I don't have the viscosity right. I'm not reading it correctly from the tables. I think I should get more partial credit. And my response is no. This is something that we've done all semester. If you've done the homework and practiced, first of all, you'll be able to read these correctly. And we do this calculation enough that you should have some sense how the numbers work. So, got some examples on homework number 10. There'll be also some problems on homework number 11 where you go through and read the tables, make sure you understand how to do that. Okay, Reynolds numbers. I'll get what I got really quickly. Reynolds number for air, 12583. 12583. Check your units. Reynolds numbers is unitless. Okay, how does it work out for engine oil? Well, I went through and calculated, and it's 364. So, first of all, what we would say is between the two, air is more likely to be turbulent, and what's going on is it is such low viscosity that that there's not a lot of cohesion forces, and we end up getting turbulence. All right, is it actually laminar or is it actually turbulent? How do we go about making that decision? And here's the criteria. Reynolds numbers for plate flow, the critical Reynolds number was 5 times 10 to the 5th. Here, the critical Reynolds number is going to be a lot lower because that fluid going through that pipe is completely surrounded. So in this geometry, frictional effects are much, much stronger, and it takes less speed or, in a sense, to get turbulent flow. So the standards, okay? Reynolds number is less than 2300. 2300. Okay, then for sure it's laminar flow. All right, 2300. That's one number to remember. Okay, there is a range of numbers where it's not fully turbulent, where there still is some sliding, but there is a little bit of random motion, and that is called the transitional region. If the Reynolds numbers get large enough, then it actually turns out to be turbulent. And for Reynolds numbers greater or equal to 10,000, it would be turbulent. So you need to know both those numbers. 2300, below 2300, it's going to be laminar. Above 10,000, it's going to be turbulent. And if you do work in heat transfer, HVAC, solar, etc., many cases you're going to try to do one or the other. If we want to ensure a lot of convective heat transfer, we're going to go for turbulent. So we're going to try to size our pipe to get the Reynolds number above 10,000. On the other hand, if you have some fluid going through a pipe and you don't want it to heat up or change temperature, you want it to be laminar, so you're going to make the Reynolds number less than 2300. All right. So in this case, the conclusion would be for air, the flow is fully turbulent. It's greater than 10,000. On the other hand, for this engine oil, the Reynolds number is 364, so it is laminar. All right, that's enough on this topic. And what you want to do is, on homework number 10, there are a few calculations where you go through and either calculate the Reynolds number for a given pipe or size the pipe to ensure laminar or turbulent flow. Really valuable skill out there in industry. Get that done as soon as possible, and then we'll move on Monday and figure out, okay, given if we have a Reynolds number, how do we figure out the convective heat transfer coefficient? All right, so take care, and we'll see you guys on Monday.